What is p of n? It counts the number of ways to write n as a sum of positive integers. So p of 4 is 5. Each partition can be drawn as a figure diagram. Stack the parts as rows of cells with the longest row on top. The shape captures the partition. From here on, we will reason about partitions through these shapes. There is a natural recurrence. Pick the largest part k and peel off the top row of length k. What remains is a smaller partition with parts no larger than k. Recurse and branch over every choice of k. This form needs an auxiliary parameter and conditional boundary cases. There is another recurrence. The left side is still p of n. The right side is an alternating sum on a single line with no extra arguments. What goes in the boxes? There is a generating function for the partition counts. The left side sums p of n times x to the n. The right side is a product over every positive I of 1 over 1 minus x to the I. Each factor lets you pick how many copies of that part to use. Take 1 over 1 minus x cubed and expand the geometric series. Each term picks how many 3's appear in the partition. Look at p of 5. There are 7 partitions of 5, and each one corresponds to one selection through the product. Every selection multiplies out to x to the 5th. The combinatorics is exactly the coefficient. Take the reciprocal. The left side becomes a product of 1 minus x to the I. Expand it and you get a sparse alternating series. The exponents are described by this formula. We will call them g sub k, pentagonal numbers. Why? Once you believe the identity, the recurrence falls out. The product equals 1, so the coefficient of x to the n must vanish. Solving for p of n gives an alternating sum indexed by pentagonal numbers. The boxes from earlier fill in, so the only question left is whether the identity actually holds. Expand the product. Each factor offers a binary choice. Take the negative x term, or skip it. A choice path corresponds to a partition with distinct parts. We call these strict partitions. The sign of the contribution is -1 to the length. So the coefficient of x to the n is the number of even-length strict partitions, minus the number of odd-length ones. Now the question has shape. Let us count it directly. For each n from 1 through 12, we list every strict partition and tag it by length parity. Then we subtract the odd-length count from the even-length count. The difference is 0 almost everywhere. The exceptions sit at 1, 2, 5, 7, and 12. 5 values, each just plus or minus 1. These are exactly the pentagonal numbers g sub k. The pattern emerged from the data. And we owe you a proof. If we can pair every even-length strict partition with one of opposite parity, the difference vanishes. The pentagonal exceptions are where the pairing fails. So our job has 2 halves. Build the pairing and find what breaks it. Pick a strict partition. 2 numbers describe its corner shape. M is the size of the bottom row. S is the length of the top right staircase. Strictly, S counts only the chain from the top right where each row drops by exactly 1. Once that chain breaks, S ends, even if more rows continue stepping down. 2 numbers, 2 cases. Move 1 is peel. When M exceeds S, we take the S staircase cells and drop them as a new bottom row of length S. The partition gains a row. Move 2 is lift. When M is at most S, we take the M cells of the bottom row and distribute 1 to each of the top M rows. The partition loses a row. Either way, the length parity flips and each move undoes the other. Watch. The partition 8764 has even length. The staircase peels off, slides down, and lands as a new bottom row. Now we read the new shape. 76543. Odd length. Reverse the move and the bottom row lifts back into the staircase. Same 3 cells, same diagram. Call this map. Peel when M exceeds S and lift when M is at most S. Apply F twice and you are back where you started. F of F equals identity. This is Franklin's involution. Now look at 543 at n equals 12. The whole diagram is staircase, so M equals S equals 3. Try peel. You would land cells underneath the staircase's tail, and the result is not strict. Try lift. You would need 3 rows above the bottom, but only 2 exist. Both moves break, so the diagram has no partner. It stays where it is. Another example at n equals 15. Peel also fails. The result is not strict. Try lift and only 2 rows are above the bottom, but we would need to take 4 cells. Same collapse, opposite parity. 2 failure modes give us 2 pentagonal series. Now lay the involution over the table. Draw in every row's pairs. Each pair pairs 1 even-length partition with 1 odd-length partition and cancels. Watch them gray out. 5 diagrams remain unpaired, exactly at the pentagonal numbers. The proof's exceptions are the data's exceptions. The shape of the involution and the shape of the formula agree. There are 2 pentagonal series. When k is positive, g sub k equals k times 3k minus 1 over 2. That gives 1, 5, 12, 22, and so on. These come from the m equals s fixed points. When k is negative, the formula becomes k times 3k plus 1 over 2. That gives 2, 7, 15, 26, and so on. These come from the m equals s plus 1 fixed points. The two failure modes give the two series. The name pentagonal comes from geometric heritage. The pentagonal numbers count dots in nested pentagons, but the link to partitions is the formula, not the geometry. Watch how p of 20 falls out from a handful of earlier values, indexed by pentagonal offsets with alternating signs. Same partition function as the natural recurrence, with the same answers. But on a single line, we started from a generating function. Franklin's involution unlocked it. We landed on a clean arithmetic identity, all because pentagonal numbers showed up. Uninvited.